So for the first one there, 5x to the 8th y to the 3rd to the power of 4. So what is, we do the number to the power first. What is 5 to the power of 4? 625. Then for each variable, when we take an exponent to another power, we multiply the powers. So x to the 8th to the power of 4 becomes x to the 32, and y to the 3rd to the power of 4 is y to the 12. Very good. So over here is the same thing. We take the number to the power. 3 to the power of 6 is 729. Then we have a to the 7th to the power of 6, a to the 42, and b to the 4th to the power of 6, b to the 24. Now, roots are just the opposite of powers. So for number 3 here, that's a square root. So we do the square root of the number. What is the square root of 121? 11. Then for the powers, instead of multiplying, we are dividing by 2. So x to the 8th square rooted would be x to the 4, and the square root of y to the 12th, y to the 6th. Well, over here we have a fifth root. The fifth root of 32 is 2. And then for the x to the 25th, fifth root is x to the 5th, and y to the 15th, fifth root is y to the 3rd. What is really happening there with those roots is, we talked a little bit early in the course about factoring. Come on now. For example, more specifically, prime factoring. So we might have something like 60, and we'd be asked to prime factor it. What is any number that goes into 60? Just one of them. Give me one. 4. Okay, 4 goes into 60. What's 60 divided by 4? 15. So 4 times 15 makes 60. Can 4 be split into other numbers? Yes. 2 times 2. Those are both prime, so I'm going to circle them. Those are done. Can 15 be split into other numbers? 3 times 5. Those are both prime, so those are done. So 60 can be built by doing 2 times 2 times 3 times 5. That's the prime factors of 60. Well, if I throw in oops, that's not what I wanted. Something like this, 210x to the 3rd y. If I want to prime factor that, I'll do the 210. What's any number that goes into 210? Well, it ends in 0, so, well, 21 goes in there, yep. If I divide by 21, I'm left with 10. Perfect. Can 21 be split further? 3 times 7. Can 3 be split further? No. 7? Nope. 10? Yes. 2 times 5. Can 2 be split further? No. 5? No. So the prime factoring here is 2 times 3 times 5 times 7. What do I do with the x to the 3rd? Well, that's just x times x times x and the y, like that. That's the prime factoring. Not too bad, right? The reason I'm showing you this is if you don't have a calculator and you need to do a root. Like I said, if you need to do the square root of one of those days where your mind just doesn't work. This is the square root of 900. The little hamster just won't get on the wheel today. Sorry, guys. We can prime factor 900. It ends in a 0, so 900 is divisible by 10. What's left if I divide by 10? 90. Can 10 be split further? 2 and 5. Can 2 be split further? No. 5. 90. What's that? 45 and 2. Can 45 be split further? 15 and 3. Can 15 be split further? 3 and 5. Can 3 be split further? No. 5, 3, 2. So what this is 2 times 2 times 3 times 3 times 5 times 5. Square roots can be done on the factor level. A square root, what's really the index up here? We don't write it, but what's really the index there? 2, yeah. It's asking what number to the power of 2, what number squared. What I can do is I can take pairs of factors inside the root. Remember, we can think of that as 2 to the power of 2, but when we did a root, what did we do to the power? We divided it by 2, right? So outside the root, that's going to become 2 to the power of 1. This is 3 to the power of 2, so it's going to be 3 to the power of 1. This is 5 squared, so it's going to be just a 5. 2 times 3 times 5 is 30. 30 is the square root of 900. Does that make sense? Do the square root of 400. What's any factor of 400? 10 and 40. Okay, can 10 be split further? 2 and 5. 2, 5, 40. 20 and 2, 20. 4 and 5, 4. 2 and 2, 2. No, 2, no. 5, 2. So 400 is 2 times 2 times 2 times 2 times 5 times 5. That's 2 to the 4th and 5 squared, right? So that's going to become 2 squared and 5 to the 1. 2 squared is 4 times 5 is 20. Square root of 400 is 20. That makes sense? Without your calculator, calculate the square root of 324 for me. So if we factor 324, 2 to the power of 7, if you get 2, that's what, 162. You can divide by 2 again, you got 81. 81 can't be divided by 2 anymore. It's going to be 3 and 27, or 9 and 9. So you've got 2, 2, and then 4 3s, right? So I can either write this as powers as 2 squared and 3 to the 4th, or I can just do this. I can circle them in pairs. That's a 2 and then 2 3s, right? Which is going to give me 18. Double check that in your calculator. Square root of 324 is 18. One of the reasons I show you this is because if you were to go on to a 4-year degree of some sort, you'd have to take like an intermediate algebra course or an introductory college algebra course. And one of the things they would do would be simplifying these roots. Like they might give you something like the square root of 108. They don't want you to punch that in your calculator and get 10 point something. They want you to reduce it to leave it as a root and then a piece piece left over. So if you factor 108, you've got 2 and 54. 54 is 2 and 27. 27 is 3 and 9, and then 3 and 3. So if you factor this, you've got 2 times 2 times 3 times 3 times 3. You've got the 2's. You've got a pair of 3's, but you've got a 3 left over, don't you? That would stay in the root. 2 times 3 is 6 times the square root of 3. They would simplify it like that. Why is that simpler? Well, it's one of those unsatisfying answers that's about 50 years outdated. Because once upon a time, we didn't have calculators. And they didn't want to, they couldn't just punch in the square root of 108 and have the calculator spit out the answer. They had to look up these square roots on tables. Well, rather than having tables that went up to 108, they had tables that went up to, well, probably about 100 or so. But rather than, so if the table didn't go up to 108, what they could do is they could just look up the square root of 3, and then by hand multiply that by 6 to get the square root of 108. Does that make sense? It was just a matter of, that's how they did it without the calculator, so that they could actually, they didn't have to have books upon books of tables of square roots. The practical use of that really is very little anymore. I just wanted to kind of show it to you. And then we could extend it if you really wanted to. We could extend it to variables. Let's say we have something like the square root of 50, x to the 9th, y to the 17th. Well, if you factor 50, 50 ends in zeros, it's divisible by 10. What's left over? 5. Can 10 be split further? 2 and 5. 2 is prime, 5 is prime, 5 is prime. So this would be 2, 5, and 5, right? Well, the y to the 9th, that's 9 y's, or sorry, not y to the 9th, x to the 9th. You know what? I'm going to cheat and do it like this. X to the 8th times x, because I don't want to write out 9 x's. And I really don't want to write out 17 y's. But here you can take out the 2 5's, right? You can leave a 2 there. What's the square? X to the 8th would be x to the 4th, right? We'll leave the other x inside. Y to the 16th would be y to the 8th, and you leave the other y inside. Now again, we won't be quizzed on this in here, but it's a process that I wanted you to see, because there are some of you at some point that will go on possibly to a 4-year degree in mechanical design or something like that. It's one of those, like I said, it's all about patterns. And once you see that a square root is about taking 2 factors and just making it 1. You know, we had the square root of x to the 8th is x to the 4th. All that really is saying x to the 8th is 8 x's multiplied together, right? So what you're doing is you're taking every 2 factors inside and you're making 1 outside. So that's why it's x to the 4th. If it were a third root, oh, let's see here. Let's say it's a third root of 216. X to the 9th, whatever. We'll just go 216 x to the 9th. Well, if you factored 216, it's 2 times 2 times 2 times 3 times 3 times 3. Get your x to the 9th, right? Up here, for square root, we had to take them in pairs, didn't we? This is third root, so we got to take them in 3. So it takes 3 of those factors. Think of that as 2 to the 3rd we divide it by 3 is 2 to the 1, so it's just a 2. 3, 3, so 3 to the third divided by 3 is just a 3 to the 1. Of course, x to the ninth becomes x to the third. But again, that's, you got 3x's, and 3x's. That's where the x to the third comes from. There's 3 sets of 3. Like I said, the good news is it's not going to kill you in here if you don't know that. But I just wanted to show you that so you can see the next step. Part of the reason is you guys are about an hour ahead of my other group. So you guys get a little bit of extra knowledge for the semester. Now you guys seem to move just a little bit faster through the materials. Okay, so the next skill we want to review, we've talked about this a little bit, and this one's going to be a little bit more important to us. Eight times a number increased by 3 is 51. I want you to take a second in your notes and write out what that's going to look like written in. So what do you get? 8x plus 3 equals 51. So we can create that equation from the phrase. And as we go through, we're going to look at creating those equations from word problems. Well, before we get too much further into it, let's talk about what we would do with this equation. Remember, all equations start out as a variable equals a number. To understand how equations work, we first have to understand what this little simple setup is. Obviously, x stands for some missing number. 6 is the number 6. This symbol here means, well, it's called the equal sign. What does it mean? It's really hard to define it without using the word equal, right? Yeah. What it's saying is what's on one side has exactly the same value as what's on the other side. In fact, one way to think about it is doing a balanced scale. What's on one side exactly balances what's on the other side. And as I said, all equations start out like this, as a variable equals a number. And they are built from there. They get more complex from there. Some things we can do to build them are basically all of our basic operations. You know, we have add, subtract, multiply, divide. We're going to see powers and roots we've had. All of those operations can be used to build up these equations. Let's just pick something simple like adding 3. So I add 3, this becomes x plus 3. But that scale is going to tip unless I do what? I have to do the exact same thing to the other side. So I have to add 3 over there. 6 plus 3 is 9. So now I have the equation x plus 3 equals 9. A little bit more complicated equation. Now, most of the time, we're not going to be asked to build the equation. The command we're going to be given is going to be solve the equation. When you're asked to solve an equation, what they're asking you to do is to take it back apart and get it back to that basic form. Well, this equation was built by adding 3, so how are we going to take it apart? Yeah, the opposite of adding 3 is subtracting 3. Takes that piece off, leaves us with the x. But again, the scale is going to tip unless we do the exact same thing to the other side. Subtract 3. 9 minus 3 is 6. We've got it back to that basic form. X equals 6. So that's it. We've solved the equation. X is equivalent to 6. It has the same value as 6. Now in this equation, we built it. Or at least you watched it be built. So you knew how it was built, so you knew how to take it apart. The trick to solving equations is to be able to look at them and figure out how they were built, so you know how to take them apart. For example, we might have 11 equals y minus 7. To figure out how an equation is built, we find our equal sign. Then we identify which side of the equation has the variable on it. In this equation, that's the y minus 7 is the side with the variable on it. Then you ask yourself, what is keeping that variable from being by itself? Well, here the number that's keeping it from being by itself is 7. What operation is attaching that 7 to my variable? It is being subtracted. So this equation was built. What was done to my variable y was 7 was subtracted from it. How do I take it apart? I'm going to add 7. That removes that piece, leaves me with y. But again, if we're thinking of that balanced scale, this scale is going to tip unless I add 7. I would do the exact same thing to the other side. So 1 plus 7 is 8. So y equals 8. What if we're not sure? Well, this value, y equals 8, should work in that equation. So I replace y there with 8. Well, I'm still going to have 1 on the left side. There's nothing to do there. 8 minus 7 is 1. I have the exact same value on both sides. That tells me that's most likely the correct answer. Does that make sense? They don't stay that simple. Here, obviously, more than one thing has been done to my variable. I find my equal sign. This is the side that has the variable on it. There are two things that are keeping x from being alone. What two numbers are they? The 5 and the 3. What operation was used to attach the 3? Multiplication. How about the 5? Addition. Now, according to our order of operations, if x is a number, what would we have to do first? Do we have to multiply x first, or do we have to add first? Order of operation says we multiply before we add. So when this equation was built, multiplying by 3 happened to the variable first. And then 5 was added to it. Now, if you think about it, if you guys put something together, whether you're assembling a piece of furniture or putting together a toy or putting something together in the shop, if you've just finished putting it together, you've just put on that last piece, and for some reason you need to take it back apart, what's going to be the first piece you take off? Last piece you put on. So here, the last piece you put on was adding 5. So to take it apart, we're going to subtract 5 first. So that piece is gone. 3x left. We have to do the exact same thing to the other side to keep it balanced. 23 minus 5 is 18. And then we got to go back and remove the times 3. How do we remove that? Divide by 3. Now you're going to see me just do that instead of putting the divide symbol in there. So the 3 divides out. X equals 18 divided by 3 is 6. X equals 6. Now again, if I'm not sure, if I want to double check, I go up here, I rewrite my equation, putting 6 in where the x is. The 23 isn't going to change. Over here, 3 times 6 is 18 plus 5, 23. I get the same value on both sides. So, again here, here's my equal sign. Here's where my variable is. When this was built, what was done to y to build it? Multiplied by 7, and then 2 is subtracted from it. To take it apart, we're going to add the 2. So 42 equals 7y. And then divide by 7. 6 equals y. It's referred to as the reverse order of operations, but it's not a new rule or anything like that. All it is we're taking it apart, so we've got to go backwards. In your big book, I'd like you guys to try several of these. On page 368, it's exercise 14-5. 370, exercise 14-6. Page 373, 14-7. You can probably guess what's coming next. 375, exercise 14-8. Give those a shot. So the first one up here, fourth root of 81. 3, how about fourth root of x to the 12th? And y to the 28th? Y to the 7th, very good. Over here, 5x to the 8th, y to the 5th to the 6th power. When you multiply, you add. When you go to the power, you multiply. So it's y to the 30th. It's easy to confuse those. So then, down here, anything we need to do inside this set of parentheses here. So we're going to do the multiplying by 7. 7 times 3x, 21x squared. Good. 7 times negative 5y. Negative 35xy. Over here, anything to do inside this set of parentheses? No, so we're multiplied by the 4y. 4y times 2x. Positive 8xy. 4y times 3. Positive 12y. Then we got negative 12y and a positive 5x squared. Are we done? No, what do we have to do? Anything we can combine with the 21x squared? 5x squared. They're both positive, that's 26x squared. How about the negative 35xy? 8xy makes it a negative 27xy. 12y, negative 12y. There it is. Any questions? Okay. A couple of you are still working on the quiz, and that's fine. Please feel free to take as much time as you need to finish up. We're going to look at just a couple of new things here. Some things in these equations that are maybe a touch more complex, like this. When you look at an equation like this, we find the equal sign as always, and then we go to identify which side has the variable on, and it's the left side over here. But what do we notice there that's different? Yeah, the variable appears twice. Now they're both x, so that's not a big issue. But we can't solve an equation with more than one variable in it. So we've got to get it down to where that variable only appears once. Now, if we're thinking of that balanced scale here, with both of those on the same side, can we just push them into one big pile? Would that change how it balances it all? No, we should be able to do that. It shouldn't hurt anything. So what is 7x and negative 2x? What does that make? 5x. So this just becomes 5x plus 3 equals 28. From there, what do we do to solve it? Subtract the 3. 5x equals 25, and then divide by 5. X equals 5. Slightly different is this equation. Here we go to identify, find the equal sign and identify where the variable is, and we see again the variable appears twice. But this time they're on opposite sides of the equal sign. Can I push them together to make a big pile now? No, they're not on the same side. So I have to get rid of one of them. And what I usually do is I get rid of the smallest one, which is the 2x in this case. And mathematically, how I get rid of it, well, if it's positive, I subtract it. And if it's negative, you add it. Well, this is positive. We're going to subtract 2x. That's gone. We're left with just the 28 over there. But remember, because of this balanced scale here, whatever I do to one side, I have to do to the other side. Well, where can I take 2x away on the left here? From the 7x. They have the same name, exactly. 7x minus 2x is 5x. And then we have the plus 3. And of course, now that one's the same as what we just had over here. We subtract 3. 5x equals 25. And divide by 5. We can run into some other variations. What do we notice is different here that sticks out? The parentheses. Whenever we see parentheses, it should scream at us, do something here first. Is there anything we can do inside those parentheses? No. So the second question, is there anything we need to do to those parentheses? Yes, multiply by 3. 3 times 5x is 15x. 3 times negative 7, negative 21. And now we're back to that form that we've worked with all along. What do we do? Add 21. So 15x equals 45. And we divide by 15. Very good. X equals 3. Now I get asked all the time, couldn't I have just gone up here and divided by 3 here and divide the 24 by 3? You get 5x minus 7 equals 8. Well, in this case, we could have done that. It would have worked. But there are cases where it doesn't work. Like this. Here, I cannot just divide by 5. It won't work. So we have to multiply that out. So again, we see the parentheses. There's nothing we can do there. So we're going to multiply by the 5. What is 5 times 2x? 10x. 5 times negative 1 is a negative 5. We have positive 3x equals 60. So now we can combine 10x and 3x, make 13x. We have the negative 5 equals 60. And then we add the 5. 13x equals 55, 65. And then divide by 13. X equals 5. Well, I'm going to have you guys try one just to see how it goes. What's that? Oh, let's see here. try that one. We'll talk about it in a couple minutes. Let's see how it's going. Now, when we have one like this, we find the equal sign. And we can actually, we've got to simplify before we can solve. So we can simplify on each side separately. So on the left side over here, we have the 3 times the 5x minus 11. 3 times 5x, 15x. 3 times negative 11, negative 33. Now the second one we have to be very careful with. There's nothing to do inside there, but what are we multiplying it by? Negative 5. Negative 5 times 2x. Negative 10x, and negative 5 times 1, negative 5. Now, before we do anything on the other side, let's finish simplifying this. I have 15x and negative 10x makes 5x. Negative 33 and negative 5, negative 38. Now, off to the right side. Parentheses, anything to do in there? Nope, so times 2, 6x, negative 30. So now we still have the 6x. Negative 30 minus 12 is negative 42. Now we have a variable on each side. Need to get rid of one. Subtract the 5x. So yes, we got negative 38 over here. That is just 1x or just x minus 42. And then add 42 to each side. So 4 equals x. And as always, if you get to this point and you're not sure, you can go back and you put 4 in everywhere the x appears and see if you get the same value on each side of the equal sign. So on page 278, it's exercise 14.9. 380, it's exercise 14.10. 386, it's exercise 15.1. And 389 through 390, it's exercise 15.3. And we'll call that good enough for the week after you work on those.